Hello, YouTubers. In this experiment, the Virtual Organic Chem Lab, video number 4, let's explore the Diels Alder cycloaddition. So we'll go to synthesis. The program will load in a minute. We'll go to the Diels Alder, and I'm going to, one of my favorite reactions, and does not occur naturally. Blank antibodies at the Scripps Clinic in California decades ago, probably 2 decades ago, actually made catalysts for the Diels Alder reaction, but it does not occur naturally. And Otto Diels, Kurt Alder won the Nobel Prize, German organic chemist, 1950, I believe. Books are written on it. Very important reaction. And it's a cycloaddition. Well, anyway, to get started, we'll take this quinone. We'll double click on that. Notice you're seeing a solid in that flask, huh? Which it is at room temperature. And what we will do is react it with cyclopentadiene, which is a rather unstable material, but in this reaction we call it a dienophile. And the quinone is the dienophile, and the cyclopentadiene, the one I just added, is the conjugated diene. Has to be cisoid, which that is. And let's put in a nonpolar solvent, and we'll represent that with diethyl ether. Let's see if everything's there. Still didn't get that ether in there. Let's try again. Okay, want to have solvent. There it is. See the blackboard? The quinone, cyclopentadiene, and diethyl ether. Let's bring the round bottom over. We'll heat this reaction. Note the time. 3:55 in the lab is what I have. And we will set up heating mantle, reflux condenser, nitrogen gas, double click, and I'll do a TLC right at time 0. Okay, and note the 3 components, the 2 reactants and the solvent. I won't save this now, but if you want, you go to the notebook and you just say save. And if you open the notebook again, it will be there. I just double clicked it. Let's go to OK. Let me open the notebook. See, you have to be careful to hit it once. So I'll backspace and get rid of it and just retain 1. Now, normally I would ask students to put in the date, the time of the experiment, which they can adjust to any time. We're in Eastern Standard Time. That's time 0. Notice the clock's moving. And you can fast forward the time, but be careful with that. If you go too fast, the glassware will explode. So you don't want to get the experiment done in a minute or 2 when you should be developing a feel for the amount of time it would take for such a reaction based on reported rate constants. Okay, I would put down the reaction, the reactants, purpose of the reaction, Diels Alder cycloaddition, and now let's get underway by clicking the stir button. And we'll start. Now, what I will do, because I did some preliminary work on this, so what we're going to do is cautiously go ahead 10 minutes, 20, 30 minutes. Let's check now. Okay, you can see changes occurring in the TLC. But look at the blackboard. The product is forming. Now, what is that product? Let's show you. That is the reaction with 1 equivalent of cyclopentadiene. The reaction, this particular one, will not show you a double addict because you still have another double bond there, an enone on the side of the quinone. You can do a double Diels Alder, but we're only going to do the mono cycloaddition. There is still starting material, and you see the cyclopentadiene. And what we'll do is go up 10 minutes, 20 minutes. Let's see what's there now. We'll do a TLC. Okay, still reacting. I'll fast forward 10, 20. Let's check. Still reacting. If you go ahead an hour or two, be careful, because if you go too fast, the glassware will explode, indicating that you are moving at an unrealistic pace. That's how I would interpret it. Let's see if we still have starting material. Sure do. Go ahead, 10 minutes, 20. Let's see what's there. Still reacting. Changes in the TLC are occurring. I just went 10 minutes more, and starting material is gone. You can see the subtle change in the Diels Alder adduct. And you can see that you only have the solvent and the product. Now, the next thing we do is click on the SEP funnel, and we can certainly wash the product. You don't have to in this particular case, but we certainly can. And you see the lower layer is water in the SEP funnel, more dense than the ether and the adduct. Okay, so we have those two. We're going to bring this over. And we're going to then take the round bottom. You presumably have dried at this point, drying agent, and filtered. You put that back on the stir plate. Hook up your distillation apparatus by double-clicking on it. Double-click on the nitrogen. And we'll start to heat this up. Now, this is the interesting part. Notice the time where we're starting the distillation. The ether was removed by rotovap. That's not shown. It's very volatile solvent. And you're not going to be able to distill this because you have a solid. So let's see if we can characterize it. And that's where the program shows you weren't paying attention. Looking up the physical properties of starting materials and products. See, that's another thing. You should look that up. And then you find out that once you remove the ether, you have a solid. And because you did not put it in the crystallizing dish, you tried to distill at atmospheric pressure, that nullifies the reaction. See, they're not going to let you do an infrared of that. So knowing beforehand you did your homework and you know it's a solid, you would have placed the round bottom in the crystallizing dish and then characterized it with C13, mass spec, infrared, and melting point. So what we'll do, in experiment 5, we will repeat this, and we will then very carefully pay attention to the workup in this reaction. Thanks for listening. Bye for now.